think now is a good time to start. All right. If Sam doesn't get in here by the time I introduce him, I'll introduce him. Okay. Hello, everyone. Thank you all for coming here. I'm happy to see the room is quite full. Good start to the semester. And yeah, welcome to Sigma, the special interest group for math and algorithms. So feel free to ask questions about anything I talk about relating to the club or relating to any of the math I talk about. But I don't really have anything else in particular to say. So I would like my point. All right. First, I'm just going to introduce like the officers of the club in no particular order. So my name is Anakin. I'm a senior in mathematics here. As far as like some of the math and like CS stuff I did some math research over the summer at Texas State University. And then throughout the school year, I kind of do more graph theory type research. So that's kind of where my interests lie. You may know me also from Sig Pony, where I help do a lot of cryptography stuff. And I'm one of the admins at Sig Pony. I also help with coffee club stuff. Come out on Sundays, a good time. And then I'm a CA for CS 173 and 374. Oh, I can point it there. Okay. Another one of our officers who couldn't make it today is Aditya. He's in ECE and math, so if you're into hardware kind of stuff, he's a guy to talk to. He interned at some satellite startup over the summer. Did some pretty cool work. He's a CA for EC 411 and 391 for those of you who will take it. And he also helps run SIG Arch, the special interest group for computer architecture. You should go check them out. They do some cool stuff. And then as far as his other interests that are more math related, he's super into functional programming. So if you ever want to get into stuff like Lisp and any other functional programming, talk to him. And he's also into cryptography. And I'll introduce Sam. Oh no. Oh, he just okay. Sam's another one of our officers who I guess isn't here right now. He's a PhD student in computer science, just started this fall. He does computational geometry with Sariel Harpeled. He's a professor here. Oh, Sam, you want to introduce yourself?
Hi, I'm Sam. That's like I like
no, you're
it's like, oh shit, it's 4. Hi guys. I was an undergrad last year when I was also someone to help make this stuff. I am now a CS PhD doing computational geometry and other CS theory with Professor Sariel Hartwell. And I also do stuff in Sig Pony, and I'm quite the security guy. So yeah, I'll be giving a talk sometime later this semester, but that's my introduction.
Yeah. Standing room only. And then Sam, if you want to talk.
Yep, my name is Sam. I'm a CS major, but I also take math faculty for some reason. I'm also part of the Sig Pony cryptography gang, and I help run the admin team. And I also help run ACM's infrastructure team, like general software engineering stuff. I'm a CA for CS 341 and 173, and I do pilot research. It's like with Professor Victor Mohammed. Oh, and to summarize, an intern at IMC Trading, do software engineering. I do a lot of things. Good questions. Feel free to ask me.
All right. And then, any further ado, you'll notice that this list, if you've been here for the past couple of semesters, this is getting smaller because people graduate. And so this is also going to be my last year here. I think this is your last year here as well. Sam's going to be here.
I'll be bridging the officers, but at some point I will probably need to like step away. Like I can be part of Sigma, but I can't be running Sigma forever.
Yeah. So the point is, please reach out to me either after the meeting, before a meeting, DM me on Discord. If you're interested in like helping improve Sigma, run meetings, if you have any other ideas, I want this club to exist for after I leave, and just plenty of opportunities to improve this club and help make things better. So, and you all are here, so I presume you're interested in the club, so I'm gonna keep it going. Please reach out. But yeah. Without any further ado, as tradition, our first intro meeting is always something related to Fibonacci. And I'm hoping to use Fibonacci today to introduce codes and coding theory. So, just as a quick refresher, or I guess before a refresher, why do we care about coding theory? So everything you do online involves sending and receiving messages over probably some long cable running out of under the ocean, or sending stuff over the internet. And the point is, the real world exists. And as much as mathematicians and theoretical computer scientists don't like to think it does, it's a reality, quite literally, that we have to deal with. And when you send messages, maybe by some act of God, some force of nature, bits get flipped in your message. And it'll be really annoying if whenever someone else tried to pay with something with their credit card, a number's flipped and it was now your credit card. So, how do we make messages robust to errors in whatever robust means, and it can change on context? How can you make messages that we send online robust to errors using mathematics? And this is quite literally used millions of times a day. So by being a math club, actually kind of relevant. So the end goal is we're going to try to assign the natural numbers, so 0 through whatever, some sort of code word associated to that natural number, and we want it to be unique. And we want it to have a couple of properties. We want this code to be quick to compute, right? Like I said, this happens in your computers millions of times per day. So if it's not quick to compute, then your using of the internet will be quite slow, and no one likes that. One property you're going to see is something, how this code is going to vary in length, right? If you think about if you just think about like the letters and we use every day, certain letters appear more often than the other, right? But on rare occasion, we need to deal with some special characters, right? We would like the letters that appear more often to be shorter, for efficiency, and then if at that cost, the stuff that we use less often will be longer and harder to compute. And like I said, we want this to be robust to errors. So if some error happens in data transmission, then we can recover those errors, or at least deal with them in some sort of sane way. And it turns out the Fibonacci numbers will end up doing all of this for us. So the Fibonacci numbers, which I'm sure people have seen before, but it's a very simple recursive sequence, right? Where we start with 0 and 1, and then to get the next number, we add the previous two numbers, right? So 0 plus 1 is 1, so the second Fibonacci number is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, blah, 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 right? And we get this sequence, which I'm sure many of you have seen before, but don't worry exactly about what the numbers are, but we have this recursive definition. So, a mathematician by the name of Zeckendorf came up with this theorem in, I believe, was it 1872 or 1972? One of those. The point is, he stated that every single natural number greater than or equal to 1 can be expressed as a unique sum of non-consecutive Fibonacci numbers, where we take the second Fibonacci number 1 and beyond. So we're not going to use the first 0, 1. We'll use 1, 2, 3, 5, etc. The point is, you can give me any number, and I can uniquely decompose it into such a sum. If we allowed 0 and 1, we would lose uniqueness, right? Because we could always replace the 1 with either F1 or F2, and then obviously if you add 0 to anything, you would get the same number. So that's why we're not gonna allow the first two Fibonacci numbers. And we're gonna call this sum a Zeckendorf sum. He's the guy who made it. So just as a couple quick examples, right? 4 can be uniquely written as F4 plus F2, so 3 and 1, right? It can also be written as F3 plus F3, but remember, we don't want to allow consecutive or the same Fibonacci numbers. We want non-consecutive. So that F4 plus F2 is unique, and then 64 can be written as F10 plus F6 plus F2, and you get the summation. Right. So I'm going to prove to you first that the existence of such a decomposition is true. That no matter what natural number is, however big it is, I can always find a summation. So we're going to prove it by induction, because recursion is induction. As I'm sure some of you have heard before, we've taken 374. If you haven't, it doesn't matter. So we're going to start with small cases, and we're going to build up to larger and larger cases. And so we're going to take some natural number n, and we're going to assume that for every single natural number less than n, our decomposition already holds. And there's two cases. So if n is less than or equal to 4, then here are your decompositions. They just exist. And it's not hard to see that these are the only ways that you could do such a decomposition. Okay. Then the next case is if we take n greater than 4 and it's already a Fibonacci number, then we're done. 55 is a Fibonacci number. There's only one way to represent it. That Fibonacci number itself. So again, we're done. But the more interesting case is what if we take a number larger than 4 and it's not already a Fibonacci number. So since it's not already a Fibonacci number, since the Fibonacci numbers are an infinite sequence, there exists some smaller Fibonacci number and some larger Fibonacci number. So we know that n minus the smaller Fibonacci number is strictly smaller than n, because it's just subtract the number, you get a smaller number. And by induction, remember we assume every single number smaller than n has some sort of Zeckendorf sum. So we know this exists. So now you have the sum for n minus fi. But some quick arithmetic yields that if we take n minus fi and add it to fi, well, we get n, those two cancel out. But n, like we said, is smaller than the ith plus 1 Fibonacci number. But what is the ith plus 1 Fibonacci number? Well, it's the sum of the previous two. So we get that n minus fi is less than fi minus 1. And what does that tell us? Well, that means that this sum of the Zeckendorf sum of n minus fi does not contain fi minus 1. Does this make sense? Right? Because you can't represent a sum of numbers by a bigger number. So we can take this sum, which doesn't contain fi minus 1, and append fi to it, right? And we get that n minus fi plus fi is equal to n, and we get this non-consecutive sum. That makes sense? Everyone see why it's non-consecutive? All right. I also claim that it's unique. I've only shown existence. We all have lives to live. I'm not going to go over uniqueness. You can look up the proof. It's kind of annoying, but believe me, it works. Okay. So what was the benefit of looking at that proof? Well, it actually allows us to design what's called a greedy algorithm. Rather than trying to brute force every single combination of sums of Fibonacci numbers to find this sum, because we know if we find the sum, that's a unique sum by the statement of the theorem. But brute forcing it is hard. I would not like to sit down and figure out which combination of Fibonacci numbers sums up to 1,000,001. I don't have the time for that. But we can use what's called a greedy algorithm to find a fast way to do this. And the proof of the theorem actually kind of hints at us on how to do that. So we first should find the largest fi less than or equal to n, right? That was one of the key steps of our inductive proof. And then we also know that we can choose this Fi because we know that this largest Fibonacci number appears in our sum, right? And so we can pick that, and then we can immediately skip Fi minus 1. So once we find this largest Fibonacci number, we're done. We find the top number, and we can now find the rest of the sum of Fi minus 2 and below. So what we're going to do for our proof is first we're going to just pre-compute all of the Fibonacci numbers up to some fixed sum. Now, what was our end goal? I want to encode messages. And characters in your computer are encoded by something you've probably heard of called Unicode. It's these little unique identifier numbers that once your computer sees that identifier number, it can look up what text to display. And I want to display text. So there's no point pre-computing all the Fibonacci numbers past the largest Unicode value. Okay? So from now on, I'm going to assume I've already computed these values. Right? So you can just see this is like a recursive process. I'm just taking two Fibonacci numbers, I'm adding them together and appending it to my list. So now this capital F is going to contain array is going to contain all my Fibonacci numbers. Okay. And this is the algorithm. This is the greedy algorithm. So I is that largest Fibonacci number, or the index of the largest Fibonacci number, less than our current value x that we want to decompose. And we have our current representation, which we're going to encode as zeros and ones, with zeros for we're not using the Fibonacci number and ones for if we are. And what I'm going to do is I'm going to take Fi, I'm going to subtract it off my current remaining number left. So to start with x, subtract Fi. If there's any numbers left, well, we know that the next number, line 9 is a mistake, that should be at 0, but we've just chosen Fi, so we're going to append a 1, saying that we're using that Fibonacci number, and then if there's anything left, line 9, that should be a plus equals 0. That's my bad. I'll fix that. But then we're going to subtract that. But if our current Fibonacci number, this I Fibonacci number, is greater than our remainder, we can't use it. So then we mark that as a 0, and then we look at the next smallest Fibonacci number. I'm going to keep doing that until we use up the second Fibonacci number. Because remember, that's the smallest one that we're allowing ourselves to use. And I promised you that it will be fast. So how fast is it? So I guess the first step is figuring out what is I, because I is kind of how long our loop is going to run. So it's a well-known fact that there's this magical number called the golden ratio. And the long and short of it is that if we take this golden ratio, which I'm going to denote as phi, the actual value doesn't matter. I'm going to take this golden ratio, and the nth Fibonacci number is phi to the n. So rearranging that, if I want to find the largest n, if I want to find the largest I, such that the I Fibonacci number is less than or equal to x, I can just take a logarithm. How do you undo an exponent? A logarithm. So we know that I is big O of log x. Then we have this while loop, and we know that since at every step I only decreases by 1 or 2, this while loop is going to run about O of log x times. Right? Yeah.
Can you explain what beta notation?
Oh, yeah, my bad. Big O notation is what we use in theoretical computer science to kind of describe like how fast an algorithm is. So what I'm saying is that a value that is big O of log x means that I is going to be upper bounded up to some constant factor by this log x value. So it's never gonna be like exponential in terms of x, or it's never gonna be even linear in terms of x. It's gonna grow logarithmically, right, as an upper bound. So when you see big O, you can think upper bound. So you can read that as I is upper bounded by some multiple of log x. Right. So this while loop does this many iterations. And then inside the while loop, I'm just doing some subtractions and appending a value to a string. And this all takes O of one time or constant work. The work in the loop doesn't depend on the size of x. Subtracting the number, in our case, takes the same amount of time. So in the loop, it's going to run constant time. And so we're doing a constant amount of work log x number of times, which means we're doing around big O of log x work. The length of how long it takes to compute this representation is going to take at most log x time. And since at each point we either append 0 or 1 characters to our representation, that's going to be the length of our code. So we know that to encode the the x, the natural number x, we are going to get a string of length at most log x. Okay, so this is kind of where the quick to compute claim comes from, because logarithms grow very slowly. If you ever looked at the graph, even as x gets very large, it kind of flattens out. So even for large values, our work is still very quick. And it's not too hard to undo this, because remember, we're appending a 1 every single time we want to use that Fibonacci number, and a 0 otherwise. So we can just kind of read down that string and find the corresponding Fibonacci number, and we get our result back. So just and then at each loop, so we have n characters in our representation, and at each iteration of the loop, we are doing constant work. So it's going to take around big O of n time. And if you remember, the length of our string was big O of log x. So to encode and decode x, it takes log x time. So all these operations are going to be very, very quick. So just as a example, so 2 can be uniquely written as 2 can be uniquely written as 0, 1, right? We're never going to, so the first 0 is going to, the first character, the leftmost character is always going to represent the first Fibonacci number, and we're never going to use that 0. Because remember, we never use the first Fibonacci number. And then the second character is the second Fibonacci number, and or no. Yeah. So the second, so let me rephrase. This 0 is because we're going to keep going while, remember that while loop stop when I is equal to 2. So that 0 represents we're not using the second Fibonacci number. And then that 1 is that we're using the third Fibonacci number. And what is the third Fibonacci number? It's 2. What is 7? Well, 7, we don't use the first one. And then we use the and then we're going to use 2, which is the third Fibonacci number. We're not going to use the next Fibonacci number, which is 3. And then we're going to use the next Fibonacci number, which is 5. So that's where the 0, 1, 0, 1 kind of comes from. But if you think about it, remember, we want to send messages across a wire. And I want to be able to tell, if I get 0, 1, 0, 1, how can I tell that this corresponds to either a 7 or maybe 2 2s concatenated with each other, right? I can't tell. So what's my solution? I'm gonna add like a comma. Because remember, one of the ideas that we got from the proof, or from the statement of the theorem, is that there are no consecutive Fibonacci numbers. So I know I can never actually see consecutive ones. So I can append an extra one, and I can get my, and I can know that's where my current word stops. So this, so each two is a 0, 1. I'll append a 1, and I'll get 0, 1, 1, 0, 1, 1. Right? But this 7, I take 0, 1, 0, 1, append a 1, and I get that. The idea makes sense? It's kind of encoding. Is anyone okay? And so, oh yeah.
So will it always start with 0, 1? 5, right? No. It wouldn't. But was it all
No.
in?
Yeah, it'll always end in yeah, it'll always end in 0, 1, because it always ends in 1, our largest Fibonacci number, and we know the value before it can't be used.
Okay, so it always ends in 0.
It always ends 0, 1. What comes before that we don't know, but yeah, it's a very good observation. So how am I actually doing my encoding? Well, I can compute the Zeckendorf representation. I'll just append a 1. And then how do I decode this? Well, I can take my representation. I know the last character is a 1, my comma word, so I can remove it. So take off that last character, and then decode it. So I get this encoding and decoding. And since all I'm doing is adding and removing a single character, the work is the same. It's still going to take log x to do this sort of encoding and decoding. And then how do I encode a whole word? Well, I'm just going to encode it character by character. So I'm going to take my letter, and then this function ord, like order, is going to be give me my Unicode value. So this is the same thing as ord from Python. If you're familiar with that, that's why I called it that. But it basically takes in a character and gives me the Unicode value, which is going to be some natural number. So I'm looking at the ith character in my message m, finding its value, and then I'm taking the encoding off that value. And then to simplify my life, just for the runtime analysis, we know that this is going to be some Unicode value, and it has some maximum. So I'm just going to say this actually runs in constant time as like, since we know it's never going to be larger than some value, right? If you remember, encoding it takes longer and longer, since it grows logarithmically in terms of x, it takes longer and longer the larger the natural number is. But we know there's some maximum Unicode value, so we know it's always going to be less than that maximum value. So I'm going to call that an upper bound. If that doesn't satisfy you, more precise analysis you can do probabilistically depending on the distribution of characters in your language. I don't know the distribution of how to find the distribution of characters in a language. Ask a Ling major. I don't know the probabilities of certain letters, so I'm not going to do that analysis. It'd be kind of awful. So since each encoding, I'm going to say takes constant time, encoding a message with n characters will take O of n time. I have to encode every single character, so it's going to be upper bounded by that work. I can't skip anything. All right. And then decoding is kind of annoying. So I want to recover my message M, and I have this code word. So I'm going to let I kind of be like our current character in the code word. And I want to find the smallest j such that the code has 2 consecutive ones, right? So j and j plus 1 are 1. Because remember, if I have 2 consecutive ones, I found the end of my current word, right? so then I'm going to take my current word, right? So from I up to those two consecutive ones, I'm gonna decode it. And then you can take the natural number and Unicode value and get the character back.
Yeah, it's in the current character.
Yeah. So like code J is like the jth character. So then this line I'm looking at the finding two consecutive ones, right? Because if the J and J plus one character are one, that's what I'm saying here. And then I'm just finding, so then I'm isolating that. So rep is now currently that isolated chunk of text. And then I'm decoding it. And then I get some natural number out. And then to get some natural number out, I'm going to find the Unicode value and then move on with my life and start decoding the next characters. And then by kind of very similar logic, I know each character is going to I have to look at every single character in my code and decode it all. And each code word is gonna be of some maximum length, since I know that each word is going to be of some maximum length. So everything in this while loop takes constant time. So for this while loop, it's gonna run at most n times. So I'm gonna say upper bounded by n. Yeah.
You say before that,
Right, but we're encoding characters, you know, some like string. Maybe you're encoding like a sentence, you're encoding your credit card number, whatever. Each character has what we call a Unicode value, which is your computer's understanding of like, because your computer doesn't read words, it reads numbers. And so Unicode is a way of uniquely mapping characters to numbers. So any character you type is going to be some Unicode character. And there's a maximum largest Unicode character. It's like a million, like 10 million or something awful like that. But it's some constant, largest constant. So we know that x's are going to be larger than that constant. And log of a constant is also constant, right? So to simplify my life, I'm just assuming that log x is a constant. Just because the analysis of that's going to be really bad. Why is n being assigned to the decoded value of rep? Because I made a typo when I was typing this slide late at night. I'll fix it. That should really be a different variable. Because n I'm using is like the length of the word, not the actual number. There are mistakes. Please call me out on my mistakes, like, because they happen. Yeah. Oh yeah. Because I know J plus 1 is the end of the commas, and then J plus 2 is next word. Okay, you're right. Okay. I'll fix that. And then also, like, by the way, I've implemented all of this in Python as well. I know the Python code works. So linked on the club site, cstheory.org/meetings, is Python code to actually do all of this encoding and decoding. So you can encode any message you want, you can decode any message you want, you can find those Zeckendorf representations, all the code is there. So if weird pseudocode doesn't quite work, take a look at the Python code. So, sure, y'all begging me, please do an example. I will. So, this word that has no extra meaning that I picked for no reason. So the Unicode value of S is 83. And in 83, I get this encoding. I don't know which Fibonacci number corresponds to which digit, but believe me that this is like the encoding. So this Zeckendorf representation plus this comma 1. I get this, I get this, I get this, blah, 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 some strings of zeros and ones. And I can just concatenate all of those together, right? And if you want to see that in action, take a look at the Python code, or I'll be happy to kind of run through some examples kind of towards the end. But that's kind of the idea. You take a character, get its Unicode value, encode it. And you can go backwards. Take this encoding, get the Unicode value, recover the character. Everything just works. So that's kind of our encoding. So, what were my claims? I want it to be quick to compute, check. We had this variable length thing, check. Remember, the length of the code word grows with respect to the actual word. I'm not fixing a length for each code. So in theory, if you don't want to use Unicode, you can use some arbitrarily large representation. We're good. So then I claimed that it would be robust to errors. And here's my claim, that if a single error occurs, at most 3 code words are lost. So an issue with a lot of early work in coding theory was that if there was some error, right, the entire message is lost. Everything after that error. Stuff might build on it previously. A very good example of this is, if you know what hashing is. Hashing works by taking some sequence of data and breaking it up into bytes, into smaller blocks of data, and assigning each block of data a unique number. The way most hashing algorithms work is that it takes a previously computed hash to compute the next one. So if an error occurs, the rest of your hash is screwed up, and you have to recompute everything. I claim for this encoding, this is not the case. That no matter where the error occurs, at most 3 code words are going to be lost. So you might have some like 3 characters kind of lost in the middle, but everything before and after that is perfectly fine. So we'll try to kind of walk through the logic of why that is. So we know that, like the observation that he made earlier, the representation ends with 0, 1, and then there's a 1 at the end of it. So we know that our encoding ends in 0, 1, 1. Just take a look at what happens if a bit is flipped in this representation. So if that so 0, 1 gets turned into a 1, 1, so either a 0 is deleted, or maybe if a 1 is inserted into by accident, or maybe something is flipped, then 1 code word may turn into 2. So you have this code word here, 0, 1, 0, 1, 0, 1, 1. This is some code word. I don't know what it is. If a bit flips, then now we have 2 code words, right? This 0, 1, 1, and then I saw 2 ones in a row, so now my next word has started, has turned into this code word of the first 3 characters, and then 1, 0, 1, 1, my next code word, right? So see how one character turned into 2, so you've lost some information. Or maybe a 0 gets deleted. So that third character 0 gets deleted. Now you have 0, 1, 1, 0, 1, 1. So now I've lost information as well. And then maybe 1 gets inserted. So where that third 0 was, I inserted 1 right before it. So now I've turned it to 2 code words. So this could be an issue. But notice that this is the worst that could happen, right? Our last 3 some 0, 1 turns into a 1, 1 by some way, and we've only misconverted that single code word into maybe 2 code words, but everything around it is fine. Notice that there may be more code words after this. They don't get affected because my ending is still fine. Right? Yeah.
So what's the example where the code words are lost? Is it just you just counts if you lose 1 and then like get 2, that counts as
Huh?
Okay.
The example for where almost 3 is lost. I think there are some edge cases where this 1, 1 at the end you turn into a 0, and then the next word can't be properly decoded. I think it happens if you consider like the smallest possible encoding. It's 0, 1, 1, and you have a bunch of those in a row. Then some stuff can break. This is containment of errors makes sense. Basically, the idea is like these comma words, these 2 1s kind of stop errors from propagating. because we decode word by word. All right. All right. This kind of brings us towards the end. Does anyone have any questions? Yeah, so in the Python code I have written, in all my examples, everything is Unicode. Unicode was kind of created to standardize typing characters in any language. And like with emojis and like weird white space characters and a bunch of other stuff. So Unicode supports that, so this would work. So yeah, so I think like if you can get your characters into Unicode, which I think covers most languages on Earth, then you can encode and decode in this way. So it's not just for English. If you were actually restricting to English, you could restrict your maximum value to something much smaller using ASCII, which doesn't support as many languages. But this is kind of like the largest case, just using Unicode.
What's wrong with 011?
Yeah, so I think that's like the worst possible case. So you have 011, and then whatever word comes after it. So if you have 011, that turns into let's say 01 or 001, then your word no longer ends, and now your next word. So then this is actually kind of like the worst possible case. But you have you say you have 011, some word before it is untouched, that's fine, and then you have a word after it. So now that 011 turned into 01, or maybe 001, that word no longer ends, and now you're converting the rest of the word that comes after it. So now you've lost 2 characters and you get 1. So that's what would happen. Parth and then
Yeah, so what we think that you
I knew the example off the top of my head and I don't anymore. I will look it up and I'll put it in the Discord. It's in the paper that this is based off of.
What about like the case where, like, if you have an error that kind of like gets rid of that one sequence and going the other two over? Like in theory, that could then result in the number of larger than character value. So like.
Oh. That gets more into the implementation. I guess like for the purposes of proof, they can get arbitrarily large. But as far as actual implementation, then yeah, you would actually have to care about in the real world. My values have gotten too big, so you might want to deal with that in some way. I don't know. I guess like the way you deal with that in the real world would depend on your use case. So yeah.
So compared to a decimal representation, which is also low of log x,
Mhm.
what would you say is the advantage of using decimal
I mean, so in the end, you want to get everything down to 0, 1 because that's just how data is.
Well, I guess binary representation also.
Yeah. So the advantage of using the second order is like we want to be able to tell when code words start and end in a kind of robust way. And the Fibonacci number, since we are you can't guarantee in binary that 2 ones never appear next to each other. And there's no such analogous claim for binary. Because any string of 0s and 1s kind of get to be some natural number, just by the way binary works, right? No matter what sequence of 0s and 1s I can get it into a natural number. So analogously, any like unique marker you have could end up being the actual number you want to encode. So then how do you how do you differentiate between a word ending as a marker, whatever you choose in binary, and the actual number, right? If 111 is your marker, how you differentiate between a 111 and that unique marker? With the Zeckendorf representation, we know because we proved it, there are no consecutive ones, so we have this unique identifier. That's kind of the crux of the issue.
This might be outside the scope, but so usually, like using the characters and getting one would be a big issue, but like I can imagine my class situation, but what are there like a lot of additional security measures?
Yeah, that kind of gets out of the scope. So for example, a very classic thing for that is there's a thing called checksums, which get used with credit cards. So if you've ever like, so there's a lot of unique identifiers of credit cards. I don't know if you've ever typed in a credit card number. If you don't type in the whole number, right, you just start typing it, sometimes the site will immediately know that you have like a MasterCard or a Visa or whatever. It's because there's like little like checksums and unique identifiers for credit card numbers. So even though, let's say I can, my 16-digit number, right? And so some bit gets flipped and I only have 15 digits. Well, immediately something else goes wrong because you can't have a 15-digit credit card number. If you do, please tell it to me. But so that would be kind of like it's kind of outside the scope of that. So that depends on use case to use case, and there's not enough time in the world to go over every single use case out there. But yeah, it's a very valid point that when you're caring about the real world application of this, you start considering all the surrounding systems. Yeah, so okay, so there's a couple questions in Zoom chat. So what do I mean when I say at most 3 code words? I'm just saying like no matter what kind of bit flipping you do for a single bit flip, there are 3 code words that you had encoded that now you can no longer decode, and I'm claiming that's the upper limit. So that's what I mean when I say at most 3 code words. And then someone else said that I think when a bit is flipped and I decode the corrupted message, I lose at most 3 encoded characters. Yeah, so that's answering that question. That's exactly what, when a bit is flipped, deleted, or inserted, you're losing at most 3 of those characters. Okay. There are no other questions. So I really only looked at kind of so I didn't first I have a funny quote. This is from one of my professors. I kind of like it. So professor said, abstract is a word people use when they haven't gotten used to something. And you've probably already kind of seen this the more and more you've done math and any sort of programming, that when you've probably first learned linear algebra or calculus, like these things seem very abstract compared to what you were doing before. You got more and more used to them, they became more concrete things. So I think it's a good attitude to kind of approach stuff with it. The stuff seems abstract, but you just play with it more and you explore it more and more and more. These things become very concrete and things that you become comfortable with. But yeah. So I kind of covered what happened when an error occurs outside of the last 3 digits, and through people asking questions, I was kind of partial for this, but try to consider some concrete cases for what happens in the case of insertion, deletion, and bit flipping. For if you look at the last 3 digits, that's 0, 1, 1 in that code word, and try to actually get a feel for what's going on. But otherwise, yeah. Thank you all for coming. So important note, next week, because building services is annoying, we're not going to be in this room. We're going to be in the transportation building of all places. I wish not, but it's where I got placed. So next week, I'm going to be talking about some of my summer research and a little bit more about how to actually get into like REU programs and undergraduate research as a whole, because I know it's something a lot of people are interested in. So keep an eye out for announcements about that. Yeah. Thank you all for coming. Please grab stickers. Thank you. You don't have an